Our next presenter is me, and I remain Jordan Suchow. I'm at Stevens Institute of Technology, which is in Hoboken, in the great state of New Jersey. So it's not easy to design experiments that can conclusively discriminate between theoretical models or hypotheses that are under investigation. The most common approach is to actually designing one of these experiments is to think hard about the range of experimental designs that you are personally familiar with, to select the one that you think is most appropriate, and to use that single design throughout the course of the experiment. That approach makes sense in certain circumstances, but in other circumstances it might be quite costly. It might be costly because the best design isn't one that's in your repertoire in the first place, or it might be that you actually learn what the right question to ask actually is only by asking some preliminary questions. Just how costly is it? I'd like to draw a very loose analogy to cups, which are a simple kind of object that we're all familiar with, and in particular, which vary greatly in how painful it is to break one of them. So on the left is a disposable plastic cup. They get the job done, they're cheap, and if you mess one up, you can just get a new one without blinking. The average one is maybe 15 cents when you buy them in bulk. In our very loose analogy, this is kind of like the small-scale psychology studies that you might run just to pilot something in the lab, maybe just testing yourself, bringing a few people into the lab in a single day. If something goes wrong with it, it's no great loss. Moving one step to the right, we have a wine glass. It costs maybe $15, and if you were to break one, there's a moment when you're genuinely upset. It's not a big deal, but you're genuinely upset for a moment. That might be in our loose analogy. That might be the case when you're running a pilot study, or maybe even a real experiment. You've brought 15 people into the lab. You've run a study, maybe 50 people into the lab, and something went wrong. There was some error in your code that incorrectly randomized things, and it was all a bust, and you have to just run it again. That happens to lots of people, and it kills a week, but it's okay in the end. One step to the right is how should I say this? A chalice, a gauntlet, a kiddish cup. These might go for $200 or so, depending on what it's made out of. This one's made out of silver. If something were to happen, like somebody were to steal this, or you were to lose it, you'd be upset. Depending on how much you cared about it, you might feel like it'd be a genuine loss. In our loose analogy, this might be something like running some of the bigger experiments that we run on a regular basis. Something that it might have taken a month or so to plan. It was something that was actually like a semester-long effort by you or some research assistants, and something went wrong with it, and it's a real sense of loss. Like you feel like you wasted time, or something happened. And then we go one step to the right, and what we have is the Holy Grail from Indiana Jones and The Last Crusade. These are the sorts of cups that are priceless. If you lose this, there is no way to replace it. I mean, this is a replica from the movie, but if you get these are the sorts of like once in a lifetime opportunities for experiments, and these are the kinds of things that we're trying to make them easier, but they're the kinds of things that many people in this audience have kind of touched a little bit, like a partnership with a huge company that's giving you access to a data source that you would never have otherwise. Your experiment gets Oprah talks about it, and all of a sudden you have 1 million people coming to your website. That's not going to happen every day. These are the sorts of things where if you miss the opportunity to get the most out of the data in this circumstance, you just won't have the opportunity again. And we're all working hard to get more of those opportunities and create things at scale, but there will always be something on the horizon that's a truly unique opportunity where if you don't take advantage of it, you've just lost something. As the technologies that support behavioral and social science experiments improve, they enable new scales of experiments, and we all just start to dream bigger. And so rather than performing tens of iterations of those small-scale experiments, we end up designing massive experiments that really stretch the limits of the infrastructure and of our capacity to think about them to the point where these experiments can only be run very few times. And if you only get one shot, then the data you're collecting is extremely valuable, and so it makes sense to spend some more time optimizing data collection. In particular, if you can double the efficiency of your data collection in a once-in-a-lifetime experiment, you now get 2 once-in-a-lifetime experiments. Okay, so I'm done with the loose analogy. Today I'm going to talk about the landscape of available techniques for optimizing experiment designs and creating adaptive designs that optimize themselves as they run. And to introduce these ideas, I'm going to start with one of the earliest examples of optimal and adaptive experiment design, aimed at efficiently measuring and comparing thresholds. So a threshold is a stimulus intensity, a physical intensity of something that is the borderline between what is perceptible and imperceptible. It is the part of the door that separates the inside from the outside. Measuring these is important in a whole range of studies, but I'll just briefly talk about one that nobody's ever run, but is just personal and kind of interesting example that maybe I'll try to use as a running example here. In middle school, I was pretty good at baseball. Like I spent a lot of time practicing it, and I was really quite good at it. I had high hopes for my future career as at least high school baseball player. Ninth grade rolls around, and one of my most vivid memories of ninth grade JV baseball, I started that season playing first base, batting first, and I was in practice. It was in a room not set up like this one, but with the same color walls. I was there reaching out to catch a ball, and it just whizzed 3 feet over my glove, and I didn't blink. I just held my hand out there. I missed it entirely. Little did I know at the time, I didn't recognize it, but I had myopia, nearsightedness, I needed glasses. And that had a pretty big impact on at least my baseball career. That at the time, I attributed that not to the vision, but to my own capacity to play. And so by the end of the season, I was playing bench. Okay, sorry. Okay, so let's imagine that we're going to design some experiment based around this experience. What we're going to do is we're going to recruit tons of people, and we're going to administer some tests to determine the threshold size of something that they can reliably identify. We're also going to administer some survey related to their causal attribution of their own performance on a variety of different things that are like sports related. And then we're going to run some sort of intervention where we're going to actually tell them the result of that test, hopefully diagnosing a bunch of them who were previously undiagnosed with myopia, and tell them, here's the quick fix, and then measure something later. Okay, so the actual task, the actual thing that we need to measure here is a threshold. We need to measure the boundary between the visible and the invisible, the perceptible and the imperceptible, and we're going to do that by manipulating the size of the thing that we show somebody, just very similar to the way that you see in a doctor's office. Okay, so let's talk about the classic way to measure a threshold. Here we have a psychometric function that plots performance as a function of the stimulus intensity. In this case, it's going to be size. These psychometric functions have a classic shape. There's a parameter that's the gamma, that's the guess rate here. If you're identifying letters, for example, it might be 1/26. There's a parameter delta that is the ceiling. It's when you see a letter that's obvious like this, you just accidentally say the wrong thing. There's a slope that determines how quickly the rise in stimulus intensity from imperceptible to perceptible, and there's a horizontal shift that tells you that is the threshold. It is the stimulus intensity that produces a certain criterion performance. Okay, the traditional way to measure this, and the way that you would do it, if you were creating a suboptimal experiment design, is using the method of constant stimuli. What you do is you pick a fixed set of stimulus intensity values along the x-axis, going from something that's comically small to comically big. You test each of them a fixed number of times. You plot this, you fit the functions of the data, you estimate threshold, and you're done. Typically, you might have to collect 40 points per stimulus intensity. You might even have to do more, and it might take you, in our study, it might take us an hour to estimate threshold. Luckily, there are many improvements we can make over the suboptimal design. In particular, you've probably had your own vision tested in a doctor's office. And though one way to use this eye chart is in exactly the way I told you, there are other ways. So the way to use it in the way that I just told you is for you to just go through this and read out loud every single letter, measure your percent correct, and you can plot roughly that function and get your the threshold. However, there's many improvements. One of those improvements you can make is by incorporating your prior beliefs. So we know that generally speaking, particularly here where most people have, if they have myopia, for example, they wear glasses or contacts. We know that it's very unlikely that there's going to be somebody who is extremely outside the bounds when actually given a test, assuming that they're wearing correct lenses. So we don't need to test the values that are very high or very low because it's not helpful. It's not helping us learn about participants. We already know that their threshold isn't far beyond where it is. So we can incorporate prior information. In our eye chart, that might mean not starting at the top, but starting in the middle. And some optometrists, some eye doctors do exactly that. They don't have you start reading the top. They just ask you to start at that row. So that's incorporating prior data. A second kind of improvement is to improve the design by actually making use of the partial data that you collected when collecting more data. So this is an adaptive design. This is one where on each trial, you place the next trial based upon what you've learned so far. So here we might say, let's test this letter. You say it's a D, you get it right. You test the next one, you get it wrong. You test the next one, you say an F, you get it right. And so we go over and over, and we are based upon some algorithm that we've decided for. We are adaptively redesigning the test as we go. There's many different criteria that you can use for these procedures, it's kind of and the different designs depend on exactly what you care about, and some of them are improvements over old ones. The traditional ones are staircase procedures. If you get a certain number right, you make it harder. If you get one wrong, you make it easier. Related to dose finding. There's also Bayesian adaptive procedures like Quest, which place each trial at your current best guess of what the threshold is. And generally speaking, there are many other techniques. Another one tries to minimize the expected entropy of the posterior probability density of the parameter estimates. That's most important in multidimensional cases. Okay. There's several other design criteria that come up in these basic adaptive designs. One question that you can ask is how far ahead should you actually look? Typically, they're myopic, which means that you just decide the next trial based upon the current stage. You just design the one next trial. But there's also procedures that have longer look aheads, where you try to design an entire sequence of trials. And there's also a question here about when should you stop? There's different approaches. Some people you can stop after a fixed number of trials or after a fixed uncertainty in the estimate. Okay, so these are the basic adaptive techniques for measuring a single threshold. But often we're not focused on measuring a single threshold. We're measuring thresholds in the context of some experiment, where really what we want is we have maybe two different hypotheses or models that predict different psychometric functions or different thresholds. And what we want to do is to design an experiment that distinguishes among those hypotheses. And so now what we want to do is we're not trying to just estimate a single curve. We're trying to figure out where can we place the next trial in such a way that it separates and distinguishes among the competing hypotheses or the competing models. This is an entire area of study in statistics. It is not easy, and it depends what the right thing to do in this case depends on every single feature of what you care about. So in particular, there are many different optimality criteria that basically define what you mean by what is the quote-unquote right place to place the next trial. The question is basically what are the goals? Is the goal to quickly determine which of the two models is best? For example, trying to find the Bayes factor, or is it to consider a broad class of models and to just be certain about which one ones you can definitely rule out. So one example is you can use this in the model selection case, or you can do Bayesian experiment design, where the goal is to actually maximize the expected value of the experiment. A very classic rule for stimulus placement in these cases where you're trying to distinguish among multiple competing models is to minimize the variance of the parameter. These kinds of designs are widely deployed, not so much in our sciences, but certainly in others. One of the most common places that they come up is in the design of clinical trials. In the design of clinical trials, typically the models under consideration are that the drug, for example, that they are testing, or the intervention that they're testing, produces a better outcome than some control, or that it does not produce a better outcome than some control, like a placebo case. And in that case, they very much want to efficiently design the experiment and do so adaptively, because their goal ultimately is to, as quickly as possible, determine whether the intervention is a success. And in particular, there's explicit costs in terms of human welfare for not getting that right, either failing to correctly identify a treatment that's successful, or taking too long, or something that's harmful, continuing the experiment. And so in these cases, people end up applying very explicit weights to and cost terms that allow you to do the optimization explicitly and create algorithms that have precise stopping rules that say, which conditions should we test next, and when exactly should we stop. This ends up being equivalent, depending on how you frame it, to a multi-arm bandit problem, and there's a host of algorithms developed in statistics and other literatures for solving that problem in different contexts. Okay. What I've showed you here is cases where what we're doing is considering a very constrained space of models. We're considering just, in this case, psychometric functions. But what happens if we don't actually have such a tight parameterized model? What if we're not studying some function that's been studied for 100 years in psychology, and instead we're trying to consider a much broader space of models, one that is less constrained and may contain a much richer set of hypotheses about the relationship between the input and output, or multiple inputs and outputs. So consider, for example, a case where what we're trying to do is, I'm going to pop up many levels too. Imagine that we're studying something like the effect of competition on innovation in teams working together. And we know that there is likely some relationship between perceived competition and innovation, but we don't know what that relationship is. Furthermore, we think that not only might there be a relationship between these variables, but there's also many other factors that could plausibly have or contribute, either having main effects or interactions or etc. So here we might have 8 different dimensions, and we may have partial or full experimental control over them. And what we're going to try to do is to design a technique that will allow us to, on the fly, adaptively design the next experiment so that it's quote unquote optimal, most informative for what we're distinguishing among our entire hypothesis space of models. To do this, I'm going to give you a 2-minute intro to Gaussian process regression. Doing active learning and active model selection using Gaussian processes is becoming more and more popular. It's rare in the cognitive sciences, but every year at machine learning conferences, people are working hard to develop new techniques, and many of these are things that we can actually directly borrow and use to do what I think we can think of as active regression. Regression where rather than collecting all the data and then doing the regression once, we're going to ask on each trial, what's the next best for the variables that we have under experiment or experimental control, what's the right thing to test next? Okay. A Gaussian process can be thought of as a probability distribution over functions. They're defined by a mean function and a covariance function, which is sometimes called a kernel. The kernel determines what functional forms are most probable. There are many different kernels. There's a linear kernel. Every function under it is linear. There's a periodic kernel. Periodic. There's a squared exponential kernel, which produces smooth functions. A particularly nice property of Gaussian processes is that they are closed under addition and subtraction. Here I'm showing just three kernel squared exponential periodic linear, like I was just saying, but they're closed under addition and multiplication. And what that means is that you can combine any two kernels to create a new valid kernel if you're combining them by addition. So, for example, a linear plus a periodic kernel gets you periodic behavior over a linear trend. Or a squared exponential plus a linear gets you some smoothly varying function with a linear trend underlying it. Similarly, you can combine them, compose them by multiplication. So the simplest case is composing a linear kernel with a linear kernel by multiplication gets you a polynomial kernel. But you can do other things like compose a squared exponential kernel with a periodic kernel to get periodic behavior where the mean is drifting over time. Going even further, because they're closed under addition and multiplication, you can define a grammar over the kernels. All the ways to add and multiply the individual kernels to form entire phrases of kernels. This is what Gaussian process active regression considers as its hypothesis space. So for each of the dimensions, you're going to define some underlying kernels and the particular ways that they can be composed, some depth to how much they can be nested, so that you kind of complexity terms that you can say, oh, only can consider two terms combined, but not 3 or 4 or 5. And now on each trial, what we're going to do is we're going to use the current data that we've collected in order to place the next trial at the combination of factor values that will be best for distinguishing among the hypotheses that we're considering. So here's one particular example of this. The top bar is the ground truth. You see that the ground truth is a periodic function with it's a periodic function. And each of the rows below it is one of the models that are under consideration. This is a linear squared exponential and periodic kernel combined up to one level of depth by multiplication or addition. And what each individual plot is showing you is the current posterior distribution over functions under that particular model. And so you can see, for example, that the linear model's posterior is linear, whereas each of the others is defined by that specific kernel. What I'm showing you here is 6 trials into the procedure. The blue dots are the data that have been collected. That's why they're the same for each of them. This is just a snapshot of one moment in time. And the red dot is the technique's suggestion. This is Bayesian active model selection. It's the suggestion about where to place the next trial. What is it guided by? It's guided by which intensity on this particular dimension will be most informative for distinguishing among this particular class of models. We've implemented this in a toolbox for Bayesian active model selection, but we are not the only ones who have been working on this. There are a growing set of tools available, some from within the cognitive sciences, many of them from people studying machine learning and statistics. I've begun to just put together a list of some of the tools that are available. And one of the tutorials this afternoon, I'll be describing some of these tools and trying to introduce people to them. Okay. The last thing I want to say about active experiment design and optimal experiment design is that there are some trade-offs involved in it. I think it's very useful for improving the efficiency of experiments. And in cases where you only get one shot, it may be the way to go. But there are 2 important trade-offs. One of them is about data reuse. So one of the things that I would think about when creating a large-scale data set or doing a large-scale experiment is that though you might just get one shot to collect the data, often what people want is to create a resource for others to use in the future. And there is a trade-off here where if you narrowly design an experiment to distinguish among a particular set of competing hypotheses or a competing set of models that have at this one particular moment, that may be less useful for people later down the line who develop better models than the ones that you're currently testing. And the data you've collected may not be the data that's most informative for distinguishing among those. In a way that you may have had a more reusable data set had you sampled stimulus factors randomly, like the default way many of us may have, or done a full factorial design. And the second trade-off is one of explainability, where there is some overhead in terms of actually just explaining the setup of experiments. I think this is something that's changing. People are becoming more used to active experiment designs online. You've all participated in versions of them through, for example, A/B testing, which tech companies all over do constantly on the web. A simple example of an adaptive design. But there is some trade-off in explainability. Okay, I'll be giving a tutorial on some of these particular toolboxes, trying to spread the use of the tools and make them available and useful for people. Great. Then our next speaker, let's put back on my presenter hat, my like moderator hat.